consider the expansion of 3 plus x squared to the power n plus 1, where n is a positive integer, given that the coefficient of x to the power 4 is this value. Find the value of n. So it will be useful to apply the binomial formula in general form using sigma notation, and it looks like a plus b when n is a positive integer to the power of n. It's sum for some variable, let it be I, from 0 up to n, and there are n plus 1 terms in total. Combinations I out of n, 1, for example, a to the power of I, b to the power of n minus I, or it may be a to the power of n minus I and b to the power of I. It doesn't matter. And you substitute I0, calculate, plus, and substitute I to be equal to 1, calculate, plus, and so on, and finally you get n plus 1 terms, and you get the full expansion. If you need some term, you consider corresponding value of y, or you may write just this and indicate that it's just general term, and if you need some power of x, you consider corresponding value of I, or if you need the full expansion, you substitute I from 0 to n and write with plus to get full expansion. So here we get the next. 3 plus x squared, and notice that here must be plus to apply formula. If you meet 3 minus x squared, you should consider it as 3 plus negative x squared, and hence a3b is negative x squared. So it becomes sum for I from 0 to n plus 1, combinations I out of n plus 1, and it will be more useful for such type of problems when exponent this power is unknown, to apply or consider x to be raised to I. So it's x squared to I to the power y, so it's just x to the power of 2i, and 3 to the power of n plus 1 minus I. And since we need term containing x to the power of 4, and you can see why we choose x, this term to be raised to the power I, not because in general we can consider x to the power of I, x squared to the power of n plus 1 minus I, but when it's x to the power of 2i, we can clearly see that we get x to the power of 4 when I is 2. So when I is 2, we get term containing x to the power of 4. And actually, we need this term to be considered. So this term becomes combinations 2 out of n plus 1, 2 because I is 2, n is unknown, we just write n, plus 1, and it becomes 3 to the power of n plus 1 minus 2, and x to the power of 4. And this term is this value, x to the power of 4, and if we consider coefficient, it's just this number in front of x to the power of 4. So we can write that combinations 2 out of n plus, out of n plus 1, 3 to the power of n minus 1 is this value. And what is combinations. The number of combinations, formula is given in data booklet. It's greater number factorial divided by the smaller factorial and greater minus smaller factorial. Let's try to simplify it. 2 factorial is just 2 and it's n minus 1 factorial. And it looks like 11 factorial over 9 factorial. When, for example, n is 10, it's 11 factorial over 9 factorial. How to simplify it? 9 factorial, it's the product of all integers from 1 up to 9, and it's a product of all integers from 1 up to 11. And you can see that it becomes just 10 times 11. 10, it will be just n, and 11, it will be n plus 1 here. So it becomes finally n plus 1 over 2, and hence it becomes n plus 1 over 2 multiplied by 3 multiplied by to the power of n minus 1 is this value. Or it will be more useful to move it to the left and equate it to 0, and it can be solved with the calculator. So you plot this graph, and n is a positive integer, so n is positive. We don't need consider negative values, and it will be x values on calculator. And since we consider equal that it is equal to 0, so you need x intercepts, and window for y it may be any value, so that y to be equal to 0 must be included. So we need x intercept of this function. So y is this function, and we need x intercept from the calculator, and n is 7. And notice that n must be integer, and if you get that n is not integer, it may say that there is a mistake somewhere in solutions. So answer is n is 7. And that's all for this question.